Alright, we've talked about some rational functions and what they look like in terms of their graphs. We know that they have vertical asymptotes sometimes, horizontal asymptotes, and oblique asymptotes as well. Now we're ready to kind of put together things that we've talked about along with other things we already know just in general about all graphs to analyze graphs of rational functions and to draw them. Okay. For this I'm going to be using the steps on page 201 to 202 in our textbook. Okay. The very first step is to factor r of x. So you want to first thing to do is factor. So we get x plus 4 over times x minus 3 over x plus 2 times x minus 2. And then we want to look for our domain. The domain of this rational function is all numbers except for 2 and negative 2. So let's say all x such that x does not equal negative 2 or 2. Okay, so that way we know, kind of what is the domain, what x values are we dealing with at all. The second step is to put your function in lowest terms, and sometimes it will already be in lowest terms, like this example. Okay, so we don't need to do anything. The third step is to find your intercepts. So our x-intercepts, of course, happen just like we know for all graphs where y is equal to 0. So if I take the function r of x and set it equal to 0 in its factored form, it happens that this rational function equals 0 when the numerator equals 0, right? Because 0 over anything is 0. And if the numerator equals 0, then either x plus 4 must equal 0 or x minus 3 must equal 0. So x is negative 4 or x is positive 3. So our two x-intercepts then are negative 4, 0 and 3, 0. Now we also want to find our y-intercepts. And of course that happens where x is equal to 0. Now you can plug your y-intercepts into the factored form. You can plug 0 into the factored form, but it's actually a little bit easier if you go back to the original, to the original form that's not factored. Because what ends up happening is we put in a 0 for x, and all of the terms, because these are polynomials, all of the terms change to 0 except for the constant terms. So if we look at the ratio of our constant terms, negative 12 over negative 4, we get 3. So that means that our y-intercept is 0, 3. Okay, now we're going to start talking about asymptotes. The very first ones we'll find are the vertical asymptotes. Yeah. Now the vertical asymptotes are going to happen where the function is not defined. So the function is not defined at x equals 2 or negative 2, so our vertical asymptotes again are lines, x equals negative 2 and x equals 2. Then we can go looking for a horizontal asymptote or an oblique asymptote. And then we can use the rules that I talked about before to look at degrees of the numerator and the denominator. So if I look at the original function here, they're both x squared, right? So since the degree of the numerator equals the degree of the denominator, so we'll say the degree of the numerator equals the degree of the denominator, that means that the horizontal asymptote is the ratio of those leading coefficients, which is 1. Because both leading coefficients are 1. So 1 over 1 is 1. So we have y is equal to 1. Now, anytime you find a horizontal or oblique asymptote, you have to answer the question, does your function cross that does it ever cross those asymptotes, right? So we have a horizontal asymptote of y equals 1. We want to know, does r of x ever equal 1, right? Because if it crosses it, it's going to attain the value y equals 1. All right? Well, what we do then is we take our function and set it equal to 1, and then we answer the question. I'm going to go back again to the non-factored form. This is always a little bit more straightforward to solve this equation. I'm going to see if there's an x where r of x is equal to 1. I'm going to multiply both sides times x squared minus 4. I end up with x squared minus 4 is equal to x squared plus x minus 12. We can subtract x squared from both sides. And then, of course, we can add 12 and we get 8. So this is telling us then that the point 1, 8 is on our graph. 1, 8 is on the graph. I'm sorry, 8, 1. Excuse me. 8, 1 is on the graph of r of x, right? And since that's true, that's where we cross that's where our function crosses the horizontal asymptote. So we can say that r of x crosses the horizontal asymptote at x equals 8. Okay, so we're going to keep that in mind when we're graphing. Alright, what's next? The next thing we have to do is we have to think about what's happening at the vertical asymptotes, right? So we're going to use a sign chart to determine what we call the behavior of r of x near its vertical asymptotes, which you remember are x equals -2 and x equals 2. Yeah. Let's take a look at a little, sketch of what we have. Here's our two asymptotes, our vertical asymptotes. And remember, the function can either go up towards infinity near the asymptote, it can go down towards -infinity near the asymptote, and for each asymptote we have to determine whether or not the function is approaching infinity or -infinity. So that's what we're talking about when we're talking about behavior. Now, what's a sign chart? Well, a sign chart is a little chart that we use to look at the sign, S-I-G-N, of the function very, very close to the asymptotes. Okay? So what we're going to do is we're going to list our polynomial. It's x plus 4 times x minus 3 over x minus 2 times x plus 2. Yeah. And then I'm going to draw a little, here's my chart. I'm going to put -2 and 2, right? These represent our asymptotes. I'm going to draw little dotted lines to remind ourselves that those are the asymptotes. And we need to think about either side of each of these asymptotes. So what happens as x is really, really close to -2 on the left here? Well, let's use the number -2.01. Then I'm going to draw a line here to split things down the middle. What happens when x is -1.99? So we're really, really close to -2. Then we're going to look and see what happens to the sign of our function when x is equal to +1.99, again, so right close to 2, and when x is 2.01. And the sign of our function is going to determine whether or not, at those places, whether or not the function is approaching positive infinity or negative infinity by the asymptote. Okay? What we're going to do is determine the sign of each. We're going to look at the sign at each of these x values for each of the factors. So these little parentheses, so the x plus 4 is going to be represented by this parenthesis, set of parentheses. X minus 3 will be represented here, x minus 2 right here, and x plus 2 will be here. Okay, and the same thing at each spot. Okay, so I just wanted to point that out to be clear. So if I plug in negative 2.01 to x plus 4, I'm going to get a positive value. If I plug it into x minus 3, I'm going to get a negative value. If I plug negative 2.01 into x minus 2, I'm going to get a negative value. And if I plug it into x plus 2, I am also going to get a negative value. So then what is the final sign of the entire function? Well, a positive times a negative is a negative, and a negative times a negative is a positive. So I have a negative over a positive gives me a negative here. I'm going to do the same thing for each one of these values, and I'm going to pause the video so that I don't run out of time. I'm going to fill them all in, and then we'll talk about what all that means. Okay, so since we have a negative next to, on the left-hand side of the asymptote x equals negative 2, that means that our function is approaching negative infinity, so it's going to look something like that. On the right-hand side, we have a positive value really close to negative 2, so it's going to be approaching positive infinity. And similarly to the left and the right of the asymptote positive 2, we're going to approach positive infinity from the left and negative infinity from the right. Okay, now we're ready to graph our entire function using all of the information that we have. So the first thing we're going to do is put all our asymptotes. Remember, we have an asymptote which we use as a dotted line at x equals 2. We also have an asymptote at x equals negative 2. We have a horizontal asymptote at y equals 1. And remember our intercepts. We have an x-intercept at negative 4, 0, as well as at 3, 0. Our y-intercept is 0, 3. And don't forget that the function crosses the horizontal asymptote at 8. So here at 8, 1. Okay. Now if we think about our what we just figured out as the behavior near our vertical asymptotes, we're going to say, oh, well, I know that the function goes through negative 4, 0, and then it approaches negative infinity, so it's going to go down like that. I also know that y equals 1 right here is the horizontal asymptote, so the function needs to approach that horizontal asymptote as x goes to negative infinity. I know that it doesn't cross anywhere except over on the right at 8, 1, so I'm going to know that it doesn't cross over here on the left. The function itself goes through 0, 3, and on the left of the vertical asymptote x equals negative 2, we're approaching infinity. So we're going to go there. Then on the left, on the right, on the left of the vertical asymptote 2, it's approaching positive infinity. So it looks something like this. Similarly, we know it's approaching, the function is approaching negative infinity. Next to the right of the vertical asymptote, it goes through 3, 0. Then it also is going to go through 8, 1. So it's going to probably do something like that. Be a little bit more smooth than I'm drawing it. But one thing that's really important to notice is that because this is a horizontal asymptote, I know that the function has to come back down and approach it as x goes to infinity. So there's going to be a little maximum, little local maximum somewhere along the somewhere before it starts to re-approach the horizontal asymptote. And this is a pretty rough drawing of this function. We could get more points if we wanted to plug some things in, but for us this is good.